Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/Linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Are you bored with writing scripts to move data into SaaS tools like Salesforce, Marketo, or Facebook ads? HighTouch is the easiest way to sync data into the platforms that your business teams rely on. The data you're looking for is already in your data warehouse and BI tools. Connect your warehouse to HighTouch, paste a SQL query, and use their visual mapper to specify how data should appear in your SaaS systems. No more scripts, just SQL. Supercharge your business teams with customer data using HighTouch for reverse ETL today. Get started for free at pythonpodcast.com/HighTouch. Your host, as usual, is Tobias Macey, and today I'm interviewing Benedek Rozemberczki about his work on machine learning for graph data, including a variety of libraries that support his efforts. So, Benedek, can you start by introducing yourself?
I'm Benedek Rozemberczki. I'm a machine learning engineer at AstraZeneca. I did a PhD in data science at the University of Edinburgh and did some research in Google AI. Right now, I live in Oxford, the United Kingdom, and I was born in Budapest, Hungary, and I work mainly on graph-related machine learning problems.
And do you remember how you first got introduced to Python?
Yeah, it's a funny story. So, because originally, I'm an economist and I mainly worked with like MATLAB and R. Both of those languages are pretty bad with strings. And when I was in grad school doing a master's in economics, there was a course in Python, and that meant that I moved from those two instantly because it was way more convenient to use. Yeah.
As we mentioned at the outset, a big part of what you're working with is graph data and doing machine learning on that. And I'm wondering if you can just start by giving a bit of an overview of when you might want to do machine learning on networked graph-oriented data and some of the types of problem domains where that kind of data crops up.
Yeah, so first I will discuss, type of problems when you already have network structured data, but I will mention this multiple times that essentially every data that lives in a metric space can be turned into graph structured data, which means that every machine learning problem can be formulated as a graph machine learning problem, interestingly. But usually the type of problems that people deal with are, in this typical web domains. So, for example, if you have a web graph, that is typically something where you can use these tools. Also in healthcare, for example, you can have certain types of interaction networks of molecules and proteins, and also, molecules themselves can be represented as graphs. Other types of problems, of course, like social network data. A lot of recommender system problems can be formulated as graph problems, as you have two types of nodes with connections between them. There's a so-called bipartite graph that's underlying that problem. Also, in other domains, for example, spatial forecasting problems are such that you can formulate them, that there is a graph that's underlying. Another thing that you can do, which I mentioned earlier, is that if you have tabular data with some smart use of, some hashing or some, locality sensitive hashing, you can generally build a graph out of your tabular data, and then you can do graph machine learning on that. And usually the type of problems that we are trying to solve, so I will use a social network example. One of the problems that people try to deal with is, predicting properties of nodes, which can be, classification of nodes, regression on nodes. So, for example, age prediction in a social network, which is a problem that can be very well solved with, a social network-based approach. Predicting edge properties. So, for example, how do I know that two people are linked when, how can I predict that when they are not yet linked on Facebook, but we might assume that they will link or they know each other. There's like a hidden connection between them. And there are problems that you want to do where you look at the whole graph level. So for example, you can ask questions like, if I have these two drugs which are represented by graphs, how can I predict that there is a certain, polypharmacy side effect for them? Or you can ask questions like, if there is a call graph of, a piece of software, how can I tell that this call graph belongs to a certain type of malware? Or, a large number of problems can be formulated. And from an abstract point of view, you can formulate these problems as GraphML problems, as, for example, node classification or edge prediction, edge classification, or graph classification. And then what you do is that it boils down to this very simple task of standard tools that we try to build, tools that I try to build.
And in terms of the tooling that's available, I'm wondering if you can give a bit of an overview about the state of the ecosystem for libraries or frameworks that are built to be able to work with graph and networked data, and how the overall approach to machine learning shifts or any differences from graph and networked data as opposed to sort of relational or unstructured data.
Yeah, so what I will start with is, just highlight a few statistical things that are interesting. So when you have graph data, one of the things that you can do is that you can do semi-supervised learning. So you can exploit the features of the neighbors that a node has, which is like a fantastic thing. So one of the things that it's like wonderful for is like, solving problems where you have a label sparsity. That's one of the things that's pretty cool, and you can do that. Another thing is that, context is based on the neighbors, and you can predict things for a given data point, even when you have missing features for that data point, which is also awesome. Most of the techniques exploit, that there is like a similarity spatially, it's called spatial autocorrelation. It's like the birds of a feather phenomenon, which is also lovely. And one of the issues is that when this, spatial autocorrelation is not positive but negative, then it's very hard to apply these methods. That's, a complicated problem. And software-wise, one of the things that was kind of important for GraphML, to start this boom, was the fact that we have a lot of good libraries for sparse linear algebra. And then there came in 2018 when people started to shift towards the use of PyTorch. So in general, in the graph analytics domain, those tools that provide, analytical capabilities, and those which are for machine learning, are very different from each other. And the type of people who develop those are kind of different. And PyTorch became dominant. One of the libraries, which is very nice, it's developed by Matthias Fay, and it's PyTorch Geometric. It's a research-oriented machine learning library. It always incorporates the newest research. It's very well designed, good software engineering principles, in my opinion. But it's research oriented very much. It's not something that's designed with scalability, production, deployment, set of mind, that we have to consider these things. Then there is other library which, as far as I know, has some support from Amazon, DGL, which runs on PyTorch and TensorFlow, so you can switch out the backends. It's production-oriented. It contains less methods. It also has tools for, dealing with knowledge graphs. And so these tools are, the main tools for parametric machine learning. And there is also a library called PyKin, which is built on PyTorch by Charles Hoyt, who is, a postdoc at Harvard. And it's a tool for knowledge graph embeddings. It contains models, loss functions, tools for training and scoring. So these are the tools for deep learning. Interestingly, the analytics tools are maintained by people who are not really involved in the deep learning community. One of the prominent tools that's really nice is GraphTool, which provides, basic descriptive statistics, but it's really scalable, pure C++. It has a Python rep, and it's maintained by a guy called Tiago Peixoto. Interestingly, JAX, the AutoDiff library by DeepMind is coming up, and they have a library that's built on JAX for this graph machine learning. For example, they have the basic models for graph convolutions and so on. And Generally, the issue is that there is no single unified library which covers a lot of things that we need, such as basic analytics, so-called graph kernel functions that can compare graphs pairwise, how similar they are, parametric tools such as deep learning on graphs, and other type of graph ML like dynamic graph ML, graph fingerprinting techniques. And usually there is no good support for heterogeneity and the temporal aspect of things. Yeah, I feel like that covers it. Yeah.
As you were describing some of the different libraries that are out there, you called out a couple of things being either production oriented or something oriented towards research. And I'm wondering if you can just give a bit of more context as to research versus production oriented libraries and sort of how the differences in those areas of focus manifest in the interfaces and the capabilities and just some of the knock-on effects that they have in terms of what you're able to do once you select a given library for the work that you're doing.
Yeah, so I would like to use an analogy from computer vision. So if you think very abstractly about these things, then the node classification problem is equivalent to the segmentation problem, the supervised segmentation problem in computer vision. The issue with graphs is that while for images you can have some very simple cropping of certain parts of the image and you can take them, for graphs you have to be able to sample locally if you want to operate on a sample. And that's an issue. And the library which is, designed with a production mindset should be able to do that data loading that does localized sampling on a graph. And PyTorch geometric is not designed with that mindset. So because of that, you have to create, boilerplate code to sample locally, batch it up properly, and that can be kind of tiresome, especially if you have a graph which has a temporal aspect, which has heterogeneity with respect to edges, nodes, and so on. DGL is more like production-oriented. It supports less models, but those are the type of things that will work well in practice, and you can easily build pipelines, for example, in Microsoft Azure using DGL. So one of the things that we did in AstraZeneca is that we use DGL. It works quite nicely. Just to give you a comparison, when I was in Google AI research, one of the issues that we had from a very abstract point of view was exactly this, how we can sample things well when you have to keep a lot of neighborhoods in a graph in memory or have key value store from which you can access, when you sample. And it's an issue. Yeah.
And then as far as the actual area of graph machine learning, you've actually ended up building a number of libraries on your own. I'm wondering if you can just give a bit of an overview of the projects that you've created and some of the motivations for building them and the story behind how you ended up building them and releasing them as open source, and maybe how they relate to each other, either in terms of inspiration or sort of the lessons that you've learned across building each of the different libraries.
Yeah, so the first library was Karate Club. The story behind Karate Club was that I had this frustration with ML research that a lot of the times you are asked to compare to certain methods, but you can't do that because methods are not implemented and the code is not open source. So I had this machine learning paper Fridays when I would take a paper, implement it, and I had a lot of tools that would run from the command line. And then when I was doing my research internship in Google AI, people told me that you should have a unified library. It should have, it could be installable via PEEP, and it would be a lovely thing to do. And then at the same time, what I saw is that certain tools, such as this fingerprinting techniques, which can learn vector representations of a whole graph, are not really available in a library. And I had a lot of tools that could do that. And then what I wanted to do is have this unified library which provides a wide range of GraphML tools that are unsupervised. And what I wanted to do is to have something that's not dependent on the auto-differentiation libraries, so everything is implemented purely in SciPy NumPy, which was kind of, looking back, a choice that had, consequences with respect to technical debt. Also, using NetworkX was not the best idea. At the same time, it gave a very nice coverage of these graph fingerprinting techniques, and to this day, people don't really write libraries which cover these things. Yeah. And then there was the other library, which was Little Ball of Fur. The goal of this library was to allow sampling on graphs. And the goal was that if, for example, if you are a company which has a large graph, then you can downsample it and test your internal tools on that smaller version. For example, if you have a browser which is running on some graph database, then you have a smaller version and you can test with that. Or if you have a library which provides some sort of graph data, then you can use it for that. And also for training GCNs, it would be nice to have something, graph convolutional network, which you can use to do batching, localized sampling, and so on. And here, one of the design ideas was that I wanted to have something where the graph operations are abstracted away. So there is a backend-based design that you just pass in a graph which is in a widely used format, for example, NetworkX or NetworkKit, and then in the backend, the sampling happens and it's scalable. Yeah. And it was a hit because it turned out that there was a need for this. We are actually using it internally in AstraZeneca to test certain, tools that we have with smaller versions of graphs that have billions of edges. And the other interesting thing was that people loved it so much that there was a whole workshop at the web conference this year about just this library and using this library in graph mining, which was nice. And then the last one is PyTorch Geometric Temporal, which is a deep learning library. And the reason for this library was that I have friends who are researchers themselves in, spatial temporal like machine learning and spatial temporal analytics, and they work on problems such as windmill output forecasting, which is a really challenging problem, or they work for companies that do bicycle deliveries or need tools for estimating, the spread of diseases and so on. And it turned out that there is no single GPU accelerated spatial temporal deep learning library out there. And it turned out that most of these methods can be implemented in PyTorch with some, tweaks of, you can exploit a lot of existing PyTorch libraries such as PyTorch Geometric. And then we started to build this library, and the mindset was that we want to have something that very well interoperates with PyTorch Geometric and can solve these, business relevant or scientifically relevant problems. The nice idea is that you can, reuse, for example, the PyTorch geometric data objects as, representations of a single temporal snapshot, for example, and, building on these tools, very existing tools heavily that you can interface with them well.
You mentioned that Karate Club was the first library that you ended up building, and you had some regrets as to sort of the foundational elements that you built on top of it. I'm curious how those lessons carried forward into your work on the other libraries and how you think about building and maintaining open source projects and just the overall sort of user experience and architectural design that go into it.
Yeah, so with Little, I kind of started to overcome some of those, problems that I had with Karate Club. The reason for the problems with Karate Club kind of were a result also that it wanted to be very, wide. So certain algorithms that I implemented have very strong assumptions about the input data, and to have a unified API, it required to enforce certain, assumptions about the input data. And then later on, what I wanted to, do is to have libraries where you can have a lot of, corner cases of the data. For example, PyTorch geometric temporal, you can have setups where, for example, the features on nodes are changing, but the graph is fixed. And we wanted to have something that, allows that and all of these interesting corner cases. One of the issues is that it's very hard to allocate time when you are working full-time on a PhD, and also, for example, you are working, and at the same time you get this feeling that the person on the other side, they are using that open source tool in their full-time job, and they are not really willing to contribute back. So sometimes I'm really surprised when people are just helping out. So for example, Karate Club heavily depends on GenSim, and someone just as a friendly gesture updated everything for the new version of GenSim. Then just a few days ago we had someone who committed a new data set for PyTorch geometric temporal, which is like the bus traffic in Uruguay, like in Montevideo. And I was so shocked that, they take the time, they write the test, they write proper documentation, they set up everything on Read the Docs. And I was like, whoa, this is nice. It's nice to have contributors like that. But yeah, it's very hard to, find this balance, how much you have to go after, individual needs that people have. And yeah, the other thing that is really nice to have is when people who are researchers, they see that there is this nexus of, graph sampling. And then what they say is that, okay, then what I will do is that I will open source my code as a part of this library, and they contribute.
You mentioned that you recently finished your PhD program, and I'm curious how much of your research work you were able to complete using the open source libraries that you were building, and just the kind of relationship between these open source projects and the PhD projects, and the kind of pressure towards publication, and what your experience has been in terms of how much weight the software holds in the kind of academic ecosystem.
Yeah, so that's funny. So both Karate Club and Little Ball of Fur ended up in my thesis. One of the external examiners was actually a guy who built something on top of Karate Club for community detection, which was very nice. But yeah, I feel that it helps you to build social capital, that's for sure. Also, people who interviewed me for AstraZeneca, they knew these tools. Some of them was using these tools actively, and just as tools. So as a researcher, you want to build things that allow you to iterate very fast. Because of that, right now when I'm writing papers which do these typical tasks such as node classification, graph classification, I can reuse my own tools. So for example, we wrote a paper on combination therapy for cancer, and because it used graph structured data, it was very easy to run benchmarks with my own tools. You know how to do the data engineering, and it's just one afternoon and you have a whole table of results.
In terms of working with network data sets and these graph structures, I'm wondering if you can just talk through your overall workflow of going from, I have this data set, or I need to acquire this data set and clean it up, to having a sort of trained model that you're able to build predictions on and, gain confidence and just sort of.
So one of the issues that you generally have is this question, how large is the graph, whether it fits in memory, and whether it fits in memory of a single GPU. So for example, there is this new tool called cuGraph by NVIDIA. I love that idea. So what they did is that they ported the NetworkX API. It literally looks like you're writing NetworkX code, but it runs on a GPU and you can do your analytics. It's a Python library on a GPU. And usually the question is whether you can do this, that either you can do in-memory analysis with. So the question is whether you can do in-memory analysis on CPU or GPU. That's the first question. Whether you have to, come up with some smart way to do sampling. That's a big question always. And also some other aspects whether you have available node features, edge features besides the graph itself and the target variable. So these are kind of things that have a very early impact on what you are going to do. So the type of things that you can use. I have this tendency that if you are doing something that's not research oriented, it should be the simplest tool that can solve that problem. Like for node embeddings, deep walk is going to work. For graph embeddings, graph2vec is going to work. For graph convolutions, the simplest models give good results. And also early on, you have to decide whether you want to use the graph for some sort of data fusion and like doing like exploration on that. And finally, one of the like interesting things that kind of came out of like working in this domain for years is that you have to very early on, measure feature importance based on spatial autocorrelation, whether it makes sense to include something because it's not just like the correlation between, for example, an outcome, a feature that matters, but also like what happens if I consider a feature, the average of that feature in a neighborhood and so on. And one of the like tools that's really missing, at least I feel like it is like tools that can measure spatial autocorrelation of features. And, you have to write code manually for that when you do exploratory data analysis, for example.
As you're working through these problems of building a machine learning model that is relying on these networked data sets, I'm curious, what are some of the unique challenges that are posed by these connected entities and just some of the difficulties that you've had to overcome in the process of gaining expertise in working within this problem space, and some of the useful tricks that you've built up over time as you've spent more time in the sort of problem domain of working on these graphs?
Yeah, so like one aspect is that the meaning of, for example, distribution shift and like the meaning of like what happens when you're in a dynamic setting is very different. So for example, it might happen, just to give you a social network example, that nodes and edges that are arriving in a dynamic setting form a completely new community where these very salient spatial autocorrelation patterns are very different, for example. That's one issue. Then another issue is that if the nodes are kind of heterogeneous and they have different data modalities, then you must have, a way to integrate that. So for example, if you have like a protein-drug interaction network, then the types of features that you have for drugs and for proteins, it's going to be very different. Or just to give you an example, like when you have, multimodal nodes, when you're, for example, something like YouTube, or you're working on like data that has that aspect, that's like, really challenging. And then of course, like the graph itself has certain like issues that you have to overcome. So in most graphs, you have this like phenomenon called like the short effective diameter, that even if you consider like a few steps in a neighborhood, you can reach most of the other nodes. And it's suddenly something that's original. The graph itself is extremely sparse, but suddenly if you have this like consideration of larger neighborhoods, the set of the neighbors explodes, which is like an issue. And then you have to come up with ways to deal with that. And yeah, these are general issues. And then of course, like you can have settings where the edges themselves don't have the same, reliability. So just to give you an example, in AstraZeneca, we deal with edges on knowledge graphs that are generated by NLP, and they are not based on some ground truths, and that's like a completely different, level of confidence that you can have for that.
It's interesting having to build your machine learning model on an already derived data set that's been processed, that's been generated from another machine learning model.
Yeah, it's troubling. And the other thing is that you have to create these ablations, like what is the gain that we have when we include these noisy edges, for example, like...
And another interesting aspect of graphs is that because of the fact that they are inherently connected and that there are inherent relations in them, I'm curious what your experience has been as far as how parallelizable the machine learning execution can be, and how you're able to break down the graphs into sort of discrete chunks for being able to run in parallel to try and speed up training.
Yeah, so usually how these pipelines operate, I can give you two examples. It's going to be very computer science oriented, but like one of the like algorithms that does node embeddings, it's like the following idea, that you have multiple random walkers in parallel on a graph. They generate these sequences of nodes, which are treated as sentences. And of course, it's very easy to run that in parallel. And then what you have is that you learn the embedding based on the sequences by applying, the Word2Vec skipgram. And that's also something that you can run in parallel if you have, a log-free gradient descent-based approach. And that's like a very nice design of how you can, create something that can learn like this function that maps the nodes into this embedding space where nodes that are nearby are close together. And so that's one design. Another design, I would recommend a paper which we did in Google AI research, where we essentially designed this system that calculates pruned back personalized page rank weights on the edges. And that can be done in parallel. And you can, sample locally in parallel. You can batch those, localized samples together, and then you can train a graph convolutional network with that. And that's, again, something that's easy to parallelize. The issue, again, is like how you store the whole graph in memory and how you make it sure that you can do very fast neighborhood lookups.
In terms of the work that you've done as far as building these libraries, but also building the models, I'm curious, what are some of the sort of structural patterns and design patterns that you've leaned on to be able to keep the code sort of maintainable and interpretable by, current you and future you, as well as other people who are coming to your code for the first time?
So one of the assumptions was that the primary target group is researchers or people who want to learn machine learning and have an understanding of how these tools can be used. And it's not necessarily for production, which means that you have to adhere to these, research area specific standards. So for example, if you have some tool that relies on, the scientific Python ecosystem, then it has to be scikit-learn-like. So very limited number of public methods. Those public methods should be used, in a very consistent way. And also certain hyperparameters should be preset. We don't assume that the end user understands all of the hyperparameters. Those hyperparameters should work well out of the box. So, it should be this turnkey type of library that I can just import it. And if you have all of these properties, then you can have this design where you can just switch out the import of the model, the construction of that, instance, and then the code runs still and people can try out things, how these things work, whether one of them is better or worse. And then also, whenever it's possible, use the Python dunder methods. So Python geometric temporal has these snapshot iterators, which use a lot of these, methods. And also, enforcing strong input assumptions. So the boilerplate is not on your side, but on the user's side. So they have to do the data engineering. And also that most of the, heavy lifting should be, moved out. So it's done by Gensim when it's implicit factorization. When it's large scale, graph operations, it runs on NetworkIt. And generally, I was really annoyed by the fact that no one writes tests. There is no continuous integration, and also you have no idea that what's the code coverage class by class in other libraries. So I try to, take some best practices in that sense, but, it's very hard to write good tests in machine learning. So most of the time, what we do is these smoke tests for, shapes and also having trivial machine learning problems where, that the model should be able to predict something that's very trivial to predict.
In your experience of building these models and working with people who are using their libraries and working in the space and with your job at AstraZeneca, I'm curious, what are some of the most interesting or innovative or unexpected ways that you've seen machine learning on graphs and networked data sets used?
So one of the interesting things that I have seen is something that people in Microsoft and Facebook research together did was release of a data set called Malnet. which is this collection of malware call graphs. And what they did is just like classifying the malware based on the call graphs, and the fact that you can use just that very simple representation to predict this very precisely was interesting for me. Another interesting area of research is this generation of graphs based on metric spaces, where you generate this similarity graph and then you can use semi-supervised learning on that. And that seems to work very well when you have this label, scarcity, or it's very expensive to get labels for that. And in the last 2 years, it's like a very active research domain, which has a lot of practical applications, and not just, this like machine learning theory research, but something that seems to, scale well and has a lot of practical applications. And then there is this like thing that we do also in AstraZeneca, is that you have a graph which has some sort of, heterogeneity, like there are different types of nodes, and then you can have multimodal data on those nodes. And then the question is, how do you integrate that? How do you fuse that?
In your own experience of working with this graph data and doing research on machine learning with networked data sets, I'm curious, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process, as well as for building these open source libraries to help yourself and other people in doing research on these problem domains?
Yeah, so one of the lessons that I learned, it's not about GraphML, but it's about a lot of people in machine learning don't understand the algorithms themselves, which is sometimes scary to see. So I get a lot of issues which are like, how can I use this to do, I don't know, this or that type of problem, which you can't solve with that tool, which is sometimes funny. Yeah, another thing is that people are not really good at recombining these ideas, which was also surprising. One of the things that I realized is that people need much more, hand-holding, notebooks, examples, and that is something that people love. If you have, for example, a model class, then there should be an example with that. There should be a notebook with that. Yeah, one of the things that I realized, that I came with a background that was in statistics and econometrics, and because of that, I had a strong awareness, what are the basic principles, such as let us say, residual autocorrelation and things like statistical phenomenon. And it was really surprising to see that people who developed these models, and some of them very important, cornerstones in this domain. And yet they didn't understand that model fails to capture something or has a certain, specification issue and so on. And that was also interesting to see. And one of the last things is that, we put a lot of effort into beating state-of-the-art models, while it's very easy to create algorithms and tools that are very simple, easy to understand, and very hard to beat, which are scalable, work well, and, these are the ideal things for actual, production machine learning.
In terms of when you're working with a networked data set, or if you're building a machine learning model and you have the option of representing a data set as a graph or as a maybe more relational structure, what are the cases where you would either choose to change the representation to not be in graphs, or also conversely, what are the cases where a graph approach might be the superior and more easily manageable way to build these machine learning models?
I feel that the data scarcity aspect, the labeling aspect, is something where the graph-based approach can help a lot. When it's not going to help is when you don't have this birds of a feather phenomenon with respect to features and labels. And those are kind of the pitfalls for these methods. And people are not checking for those assumptions for some reason. They don't understand that these techniques, most of them assume that there is this, strong spatial similarity in the feature space and the label space. So like there's notorious examples. For example, just to give you an example, like predicting gender based on a social network is a really hard problem. So surprisingly hard compared to predicting the age of people. So just by averaging out the age of your friends, you can explain roughly 50 to 60% of variance in age. While for gender, even with something very complicated, you can barely have an area under the curve of 0.55 or something like that.
In terms of your own libraries and tools that you've built to help yourself in working through these problems, what are the cases where you would decide not to use them and instead lean on a different set of tooling or technologies?
So for spatial temporal learning, Python geometric temporal is the only tool out there, so there isn't much choice on that side. Little Ball of Fur works very well with the network kit-based backend, even on large problems. So when we saw in AstraZeneca that we can scale it up to the whole graph and downsample, we have this knowledge graph and downsample that Little Ball of Fur, that was really nice to see. At the same time, like design of Karate Club means that it's like research oriented and it doesn't work well when it comes to, industry size node embedding problems. But, side note that some graph fingerprinting methods that I implemented in that library, because they work in this inductive manner, can be parallelized easily, executed just on blocks of graphs, and because of that you can do large scale machine learning with that. So the people who released the malware network dataset, which consists of like 2 million graphs, some of the graphs has like hundreds of thousands of nodes. So it's large graphs. It's like, 10 terabytes of data. And they managed to use Karate Club on that, the graph level embeddings for each of the graphs. They had a very smart way of distributing it, which was interesting to see. But what I would say is that the tools that I created, Karate Club is purely research-oriented, Little Ball of something that you could use in production, and also Python geometric temporal would work in production. So we were able to train forecasting models using more than, 5,000 windmills, which are located in one of the Scandinavian countries, which is nice.
In terms of the overall space of graph ML and the sort of capabilities that it provides and the types of problem domains that it's conducive for, what are some of the sort of interesting and upcoming trends that you're keeping an eye on? And what are some of the areas that you're excited to work on, either by extending your existing libraries or building out new tooling or just doing your own research in the space?
So one of the interesting problems that we are trying to tackle with the people involved in Python geometric temporal is this issue that on most social networks, the time difference between events is not constant. So for example, the examples that I mentioned, the epidemiological forecasting problem, windmill output forecasting problem, there the time differences are constant. But in a lot of settings, it's not true. It's very hard to handle because you have, spatial domain, temporal domain, and you have to be able to have the right type of data structures and defining models on that, which can, operate on that type of data. So that's definitely a direction that we are working on. So Python geometric temporal, it's like this community effort with people from the University of Cambridge and Oxford, and we're working on that to make that possible. And one of the things that I want to do personally is to have other types of backends for Little Ball of, such as, like this scikit network, iGraph, Graph Tool, and these classical graph analytics libraries as backends. And personally, what I would love to do is have a library which can calculate different measures of spatial correlation on a graph, because it's something that I have to do. I have to write code for that, and most probably other people have the same problem. And it seems to be, again, a niche area that no one tries to tackle.
Are there any other aspects of the libraries that you're building and the work that you're doing in GraphML or the overall space of machine learning on graphs that we didn't discuss yet that you'd like to cover before we close out the show?
Yeah, I feel like that one of the interesting aspects is that it intersects a lot with geometric applications of ML, and because of that, it might be interesting to get at those more general cases and how, for example, graph ML relates to computer vision and processing of sequences. It's just like something that I would like to mention, and also uh, explainability on graphs seems to be a very hot topic in the last 1 year, and there are beautiful papers and good tools to do explainability at the instance level on nodes and edges.
And are there any particular resources or reference material that you would recommend people look to if they're trying to learn more about how to take advantage of networked data sets and build machine learning models across them?
Yeah, luckily this year two textbooks came out, and I feel like that most of the models that are described in those textbooks are available in PyTorch Geometric and also in DGL. Out of these two textbooks, I would recommend the textbook by William Life Hamilton, who is a professor at Mila. If people will search for it, they will find it. It's a very generic graduate school level textbook for graph representation learning. I would recommend it. It's like easy read, fun, publicly available, but you can also order a hard copy with a proper hardcover if you would love to do that.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing or contribute to the libraries that you maintain, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose the movie Wrath of Man. Came out recently. It's a Guy Ritchie film, and all of Guy Ritchie's films I've thoroughly enjoyed just because you really have to pay attention to understand what's going on. And this is another one where there are a few interesting twists to it. So just had fun watching that. So if you're looking for something to watch, definitely recommend that one. And so with that, I'll pass it to you, Benedek. Do you have any picks this week?
Yeah, I would like to recommend Hunt for the Wilder People, which is a 2016 movie. It's by Taika Waititi, who is a director from New Zealand. It's a wonderful comedy drama movie about an actual real rehabilitation problem for children who are young offenders in New Zealand. It's a hilarious movie. And I would also love to recommend a research paper which has the title Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges, which is this wonderful, pretty long research paper which unifies a lot of machine learning that's out there. It's a pretty heavy read, but it's worthwhile.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing on building libraries and doing work in the GraphML space. It's definitely a very interesting problem domain, and I'm curious to see how it continues to evolve. Definitely been seeing a lot of interest in how to be able to do machine learning on graph data. So thank you for all of your time and efforts on that, and I hope you enjoy the rest of your day.
Thank you. Have a nice day.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.